Okay, I'm going to be talking about 6.4, length of curve. Length of curve, I think it's helpful to talk about area here before we get into this. With most of these things, we don't do straight up proofs, but it is good to sort of conceptually what's happening here. So once again, area is the simplest of all these geometric things because we have this idea that if I want to find the area of the curve from A to B, I start with the idea of slicing that up into a certain amount of rectangles, right? I can approximate that. Let's say I use 10 rectangles, 1,000 rectangles is a better approximation, et cetera, et cetera, et cetera. When we get to calculus, we get that idea that I can actually slice this in a number of times. The width of any one of these rectangles would be an infinitesimally small change in x, dx. The height would be f of x. So the area of one of those rectangles is f of x dx, and we integrate those from A to B, essentially adding up those infinite number of rectangles. We do a similar sort of thing when we do volume with the various shapes, whether they're discs or washers or the shells. It's all sort of the same logic, adding up an infinite number of things. Length of curve, it's really the same thing. There's just a little bit of adjustment we have to make with the notation to get this to work out. We ultimately want something of this form because we know once it's in this form we can use the old fundamental theorem of calculus, capital F being the antiderivative of that, and we know that we can evaluate it like so. So the idea when we do length of a curve, let's start with sort of the same general function, all right? So there's our function there. What we're going to do is we're going to slice it up like we're going to do a differentiable, like we're going to do a derivative. So if you think of like what we do with the derivative, right, we look at this tiny, tiny rectangle where the height is dy, infinitesimally small change in y, and the width of that rectangle would be our run, or dx, infinitesimally small change in x. And of course, when we do the derivative, it's dy over dx because it's rise over run. Okay. Now, what we're interested in is the hypotenuse, because that is basically, as we get more and more of these shapes, it's going to get closer and closer and closer to the actual shape. So for instance, I could approximate this by doing a series of these triangles and then each one getting the hypotenuse. Think about it. That's actually what distance formula is, right? The distance formula is just using the Pythagorean theorem. So our hypotenuse there, the distance, is going to be the square root of dx squared plus dy squared. Okay? Now, in typical calculus fashion, we're going to sum those up from A to B, add up an infinite number of those creatures. Okay. The problem is, as it stands, is we have something that doesn't necessarily mean a whole lot to us. So we were going to have to sort of work through this notation to get it to be something I can actually evaluate. Now, the one thing I want to say about this is that this is one of those things I definitely want you to understand this step by step. And once you see it, you should be able to reproduce it. I wouldn't expect you to come up with this on your own, okay? So the first thing we realize, of course, is we need a dx like we always have. So I'm going to put a dx out here. Now, I can't just multiply by dx, right? But I can multiply by dx over dx, right? If I multiply by dx over dx, I'm just multiplying by 1. So I'm not changing anything. And I'm doing that so I can kind of create this dx, if you want to think about it from that perspective. Okay, so now the next thing is, ultimately, I want to bring this dx under that radical. So I want this under a radical. But I can't just put that under a radical unless I square that. Now, if you're sitting here going, well, that isn't the same thing, I want to point out to you that we all know that x is not equal to the square root of x squared. The reason being is, if x is a negative, that doesn't work because we get a positive on the right and a negative on the left. However, in this case, we're talking about this dx going from A to B, so we are talking about left to right. That dx is going to be positive. So since we know that dx is positive, I can say this. So we're taking dx to be a positive. Okay? So now what I'm going to do, that allows me to bring this radical under this radical. So keep in mind, we've done this in the past. If I go radical 3 times radical 4, that gives me radical 12. Yeah, I know radical 4 is 2, but still, it's a radical 12. As long as both things are under a radical, I can multiply them. So I'm going to use that property here. So now, I'm going to rewrite this thing as a to b. I'm just going to make a big radical here. Dx squared plus dy squared. This is going to go in parentheses. And this will be 1 over dx squared. Okay, and then we have the dx outside. All right, now of course what I'm going to do is distribute. I'm going to multiply this by each one. So we can put these over ones, and you're going to see quickly that this actually gives us something that's going to have some meaning to us. Okay, so a to b, dx squared over dx squared, which of course is going to end up being 1. And here I get dy squared over dx squared, which also should be something that we can see we're going to be able to simplify. So in the end, our formula for length of a curve of the function is going to be a to b, the square root of the quantity 1 plus, and then dy over dx squared. So we're going to find the derivative and square it. And that is our formula for length of the curve. Okay, so really this is just a formula we end up memorizing. It's not much more than that. It's not like I have to go through this process every time. But once again, I want to sort of make you understand, this is something that once you see it, you should actually be able to reproduce it. If I ask you to show me where the length of the curve formula comes from, you should be able to reproduce that and certainly understand it. Okay, now one last thing I want to talk about with this. When we do the whole a to b f of x dx, this thing exists as long as f is continuous on a to b. That's it. That's all it has to be. Okay. When it comes to this thing right here, notice since it has a derivative on there, our situation is a little bit. In order to use this formula, I want to fix that. It's bothering me. Okay. In order to fix that formula, our function f must, or y or whatever, must be differentiable. So it's a higher standard from, and I guess it's the open interval as long as it's continuous on the closed. No, I think it does have to be on the closed now I think of it. Okay, so it's kind of a higher standard there. So that's our formula, or you can write it in function notation, a to b 1 plus f prime of x squared. And just like when we did the volumes, it's going to be very rare that we actually evaluate those things by hand. Typically we'll do setups. If they do want to value, usually we'll have our calculator use Math 9. So this, for the most part, these problems end up being pretty basic. So I'm going to do a couple examples, and I'm also going to get to when this thing is a problem and it's going to deal with differentiability. Okay, so I'm going to start off with a very basic example. Very basic things really just boils down to taking the derivative. Like I said, we don't even typically integrate these things because most of the time the integrals we get are going to be things we need more advanced techniques. And some of this we'll do later, but for right now, we're going to do setups and then Math 9 values. So once again, our formula here for length of a curve is given f is differentiable, not just continuous, but differentiable on that closed interval a to b, then this formula, the integral from a to b square root 1 plus f prime of x squared dx is the length of the curve from a to b. So let's just start with a very basic one. We want to find the length of the curve of f of x equals square root of x from 1 to 4. So let's take a look at what this thing looks like. By the way, if we were going to do this from 0 to 4, this would be problematic, but we're just going to do 1 to 4. So what we're talking about is I want to find the length of this curve right here. So I'm going to find this. Okay, so how do I do that? I just basically plug in this formula. So pretty simple stuff. So f prime of x is equal to 1/2 x to the negative 1/2. Okay, so that's equal to 1 over 2 square root of x. All right, and now I'm going to square that. So if I square that, I'm going to get 1 over, and that would be 4x, because I'm going radical x times radical x, which is just going to give me x. So that's simply going to be the integral from 1 to 4, square root of 1 plus 1 over 4x. By the way, if you did leave it in an unsimplified form, that's fine, as long as it doesn't specifically say simplify. And that's going to be it. And you know, you can plug in your calculator and calculate what that is. And that's it. That's length of a curve. So for the most part, when we do length of a curve, it's just a matter of taking the derivative of that function and squaring it and then plugging it in the formula. Okay, so let's take a look at when this isn't quite so easy. Okay, so let's talk about finding the length of this function, sine absolute value of x. I start with this one because it's I think a lot of you could probably think through what we're going to do here. But obviously, from -1 to 2, as we said, when we do length of a curve, we have to deal with the differentiability issue. So it is continuous. There's certainly a length, so that we're clear what we're finding here. We want to find the length from here to here. So certainly there should be a way to do that. And there is, but I have to work around the fact that we do have a differentiability issue here. Now, when it comes to something like an absolute value, something that has sort of that sharpness to it, as long as it's not a vertical thing. If it's a vertical thing, then we have to get a little bit more sophisticated. But something like this, all I have to do is break it into 2 parts. So if you remember from last year, quite often we would look at something like this as a piecewise function, and this one's pretty easy to break down that way. It's going to be sine of negative x, as long as we're talking about x less than or equal to 0. And it's going to be sine of x, as long as we're talking about x is greater than 0. So we're really just going to look at it from this perspective. Okay? So now if I take the derivative of this thing, okay, we've got to use chain rule here, so this will be negative cosine of negative x. X strictly less than 0 because it's not going to exist there. And the derivative here will just be cosine x. X is greater than 0. Okay, so now I'm just going to break it into 2 parts. So from -1 to 0, I'm going to use this top part. And then from 0 to 2, I'm going to use that bottom part. And that will do the trick there. So let's go ahead and set that up. Once again, we'll just do the setup. And then you know, that's going to be fine for us. Okay, so we're integrating from -1 to 0. We're going to use that first part here. This will be the square root of 1 plus negative cosine negative x squared, that whole thing squared. So obviously that negative will become positive. You know, do that if you want, or leave it like that. It really doesn't matter. So that's going to give us the part from -1 to 0, excuse me. And then we're going to go plus, and the part from 0 to 2. And that will be 1 plus, and then cosine squared x dx, and that's going to do it. So easy workaround for things that have that sharpness. Just break it and deal with it kind of like a piecewise. Give yourself 2 different derivatives. Okay. So the last thing, if you remember, is what if we have a vertical quality. So let's take a look at that. Okay, our last example today, we are going to deal with something that has a vertical tangent. Okay, so I go with the most basic one because I am not feeling all that creative at the moment. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. We want to find the length of this curve, and remember this thing has a vertical tangent at 0. And keep in mind, when it goes vertical for 1 point. It's still a function and all that stuff. So we're talking about finding this length right here. Now, I can't just simply break this up because this thing has to be differentiable on a closed interval. So I have to find, I can't split it up like I did with the absolute value. Okay. Now, by the way, if you're ever unsure about why we have a vertical quality, if you take the derivative of this, we get 1/3 x to the negative 2/3. So that's equal to 1 over 3. And that's x to the 2/3 power. We're getting that 0 in the denominator on both sides. Like if I think about as 0 gets larger and larger, or excuse me, as we get closer and closer to 0 from either direction, that's going to infinity. The infinity derivative is indicating that we are getting a vertical quality of some sort or another. Okay, so what are we going to do here? So we can't split it up. But what I realize is if I do this as a function of y, functions of y, I'm not going to have a problem with that, that vertical tangent. With a function of y, it will be differentiable. So if I have a vertical quality, we just have to do it as a function of y. The rare case where it's sharp and a function of y, then it gets a little bit trickier, and we'll do an example with that at some point. Okay, so function of y to the third is equal to x. Now think about what the values are here. So instead of going to x equals -1, right, I'm going to plug that in there. That's going to be y equals -1. So I'm going from y equals -1. And then 8, plug that in there, that's 2. So instead of doing a function of x, I'm going to go ahead and do a function of y. From y equals -1 to y equals, excuse me, not 8, y equals 2. And that will fix the problem. So I'm not interested in dy over dx, I'm interested in dx over dy. So that'll be 3y squared. So now let's plug that in the formula, and that's going to be -1 to 2, square root of 1 plus, and that will be 3y squared. You could call that 9y to the 4th if you're so inclined, or you can just leave it. The setup for right now is just going to be fine. And that's basically it. So to sum up, once again, if we're going to do the length of a curve, it's always going to be, the function has to be differentiable from a to b on that length that we're looking for. It's a square root of 1 plus the derivative squared. All right. If we have an issue of differentiability where there's some sort of sharpness, I would break that into 2 parts. If it's got a vertical quality, then I would do it as a function of y. Don't get the wrong idea here, because I spent most of this video talking about sort of these problem areas like the sharpness and the function of, or the vertical. So in other words, most of the time when we're doing length of the curve, you know, these things are going to be differentiable, they're going to be well behaved, and you can just sort of plug them in the formula and be done. You just have to be conscious of the fact that from time to time, you're going to see a problem that on that interval, there's going to be a differentiability issue that we have to work around. So that is 6.4.